Hi there, welcome back to another Study With Me session. My name is Amy, I'm the head tutor at Pinnacle Coaching College. So what I've got for you today is a module on complex numbers. So if you're an Extension 2 student about to hit your first HSC school assessment, this might help you. So I've broken up complex numbers into two components. First component is just purely working with vector style questions. I find that students do tend to struggle with vectors question, even now that vectors is introduced into the extension 1 course. I think conceptually it's still a difficult concept to wrap your head around. So that's what I'm going to look at today, and I'll also link down below a second module which I'll do, which is a much broader complex number hard questions. So I'm going to have a look at hard exam questions. So if you're up for the challenge, stay tuned for that. All right, let's get straight into it. So before we dive into vectors, I think we need to build that sort of basic understanding or revise. I'm hoping this is revision for you. So first of all, how are complex numbers graphed on the Cartesian plane? So if you well, basically, before you even dive in, there are two forms, right? Cartesian form and modular form you mostly work with in complex numbers. So a Cartesian form will be, for example, z is 1 plus root 3i. And the equivalent mod arc form of that will be 2 cis pi on 3. Okay, so how is that represented on the number plane? So the x-axis is basically the real axis and the y is the imaginary axis. All right, so basically they plot like coordinates. So the real part is the x part and the imaginary part is the y part. So let's say it's about there, 1 root 3i. All right, so that's where the point z is. So then the vector is the arrowhead drawn from the origin pointing towards the point it represents. And in fact, that's called a precision vector. So the length and the direction of this particular vector represents 1 plus root 3i or 2 cis pi on 3. 2 is the modulus, pi on 3 is the argument. And basically, you should know how to plot it, I hope by now, because that's important to finding the mod arc form itself. Yes, I found the modulus just through Pythagoras, so that's 1 and root 3, so Pythagoras gets you 2, and then you just use tan to find the angle. All right, I won't get into that today because that's not the purpose of today's lesson. So let's talk about vector addition and subtraction as well. Now, if you are not comfortable doing vector addition and subtraction, I highly recommend you watch my video on vectors. I've done that for Extension 1 students, but the concepts apply to Extension 2 as well because you're working with the same stuff essentially, right? I'll link it down below in this video, so go check it out if this is not your strong point. But what I will do in this lesson is just very quickly summarize and review how to do vector addition and subtraction. So in a nutshell, okay, there are two ways to add and subtract. So there's sort of the head to tail method. Let's say if you have vector A and then you have vector B, okay, so you just actually, let's do one more, right? So let's do vector C, okay. If you want to add them, they almost form like a daisy chain sort of situation. So you attach the head to the tail of the next one and you just keep going. Once you finish, join the tail of the first one to the head of the last one, pointing towards the head of the last one. That will be A plus B plus C. All right, so that's vector addition in a nutshell. What if you want to subtract? So let's say I want to do A minus B instead. So all you really need to do, so let's say, let's do it down here. So this is A, and B is originally pointing this way. So negative of that is just flip the direction of the arrow. So it's now like that. So that's minus B. Then it's basically same as vector addition. You're doing A plus minus B, linking that together. That's A minus B. Right, so that's vector addition, subtraction in a very high level nutshell sort of situation. Now, the other one I really want to show you is the parallelogram rule, because you will find as we dive into some of these exam questions in this area, a lot of it work with a parallelogram and position vectors. So you do need to understand how they kind of operate together so you know what to look for. So let's say oops, I was going to say B. Okay, so vector A, vector B, okay, typically if you're drawing two complex numbers, they're going to look like this, right? So two position vectors, tail and sitting at the origin. So how do you do addition is you complete the parallelogram. I can't draw a straight line today. Nope, not happening. Ah, that's close enough. Okay. All right, so complete the parallelogram. The core main diagonal from the telltale attachment to the opposite corner, that's your addition vector. And then the subtraction vector is basically the other diagonal, and where you point depends on what are you subtracting. If you're doing A minus P, you point towards A. All right, if it's B minus A, you point towards B. All right, that's pretty self-explanatory. All right, so I think for us today, yes, have that core understanding how vector addition generally works, but know how to do this. Yeah, know that if you're trying to add two vectors, main diagonal is your addition vector, the other diagonal is your subtraction vector. That will save you a ton of pain once you get into the problems. All right, so let's get straight into it. So all of these I've actually picked, I think there are a lot of excellent HSC questions in this area, just to showcase some of the concepts and, how to sort of combine things together. So what I've got for you, a very recent one to 18 question 11D. We've got A, B, C on the Argand diagram, so this guy here, and they represent U, V, W. They form a square. Okay, so immediately think square. Square means all sides are equal, all angles are 90 degrees. Okay, so that's incredibly important when it comes to building vectors. All right, so the first one, now we're given what U is. All right, so I'll make a note, but I'll just work it into the working later. All right, so find W. So first of all, you want to work with vectors that's attached to the origin where possible, because they are the easiest vectors to work with. Why? Because OA actually represents U. OC actually represents W, right? So there's no tricks. Very, very simple. Now, 90-degree rotation, if you take a vector, rotate it anti-clockwise, 90 degrees is multiplied by I. So W is simply U times I. Okay, so rotate 90 degrees anti-clockwise. Here's a tip for you. If you didn't know this already, if you want to rotate clockwise instead, times minus I. Okay? All right, so solving that in, so that's 5i plus 2i squared. I squared is minus 1. That's it. Simple, right? Vectors are not that scary after all. Next one, V. Now, going back to parallelogram. A square is a form of a parallelogram, right? So if you have two vectors, that main vector there is the addition vector. So if you come back to this case here, OB is the addition vector of these two. Yeah? So everyone see how it's the same thing as the parallelogram rule I showed you earlier. All right, so what I'm going to do, I'm just add a page. All right, so I'm just going to refer to the diagram I've got on the page here. All right, so what I've got is, so I'll write it in the vector form just to show you. So you can see that OB is equal to OA plus OC. Okay, so OB is OA plus OC. Okay, and they represent U and W. Right, and OB was V, so V is equal to U plus W. U was 5 plus 2i. W, we just worked out, is minus 2 plus 5i. Add that together. All right, so that's it. So just writing that here, that's 3 plus 7i. And if you look at this diagram, it looks like 3 plus 7i. I mean, it's not drawn to scale, but at least it's in the right quadrant. Okay. There we go, that's a bit better. Now, I think 1 and 2 are fairly simple, very straightforward. The third one, argument of W on V. So I think that can trip up a lot of people, especially if you don't have a good enough understanding around how modal form actually works. So let's discuss this a little bit first before we dive in. Okay. Now, obviously, you can absolutely go find the argument of W and the argument of V and actually, or you can do division and then actually find the argument. You can absolutely do that, but that's not necessary, because when you divide, argument subtracts. Yeah, let me repeat that. When you divide, argument subtracts. The opposite of that is when you multiply, argument adds. Okay, so divide, argument subtracts. Okay, so what's the argument of W and what's the argument V? Let's come back to the diagram. W is this angle here, right? And the argument of V is this angle here. So you don't need to be a genius to work out the difference between that angle. You can look at the diagram, right? So let's call that theta. That's the angle you're looking for. Does that make sense? So that's 45 degrees because the diagonal always bisects the vertex angle in a square. That's pretty much it. And given this is a fine question, you don't really need to justify yourself. It's only 1 mark. So that's pretty much it. So I will still make the note just so that you remember. Yeah. All right, so that's it. Very basic one just to warm up some of your vector knowledge. All right, so that you can see in this first question, we already see, all right, we've got a square, which is a parallelogram of sorts. Got 2 vectors and then the addition vector, and then we're also playing with the arguments and what that means on the diagram. All right, so let's look at the next one. This is an older one, 04, so we've got the diagram shows 2 distinct points, A and B, represents the complex number Z and W. Let's note that down, Z and W. They lie on a circle with radius R, centered at O. C also sits on the circle, meaning that's also R, and it represents Z plus W. We should already know that even without it being pointed out to us because you have a parallelogram, right? Or maybe put it this way, that implies that this is a parallelogram. Okay. All right, so using the fact that C lies on the circle, show that geometrically AOB is 2 pi on 3. Okay, well, I guess that's what we'll go with first. So since C is equal to Z plus W and A is Z, B is W, then we can conclude that OAC CB is a parallelogram. All right, so that's just coming from factor addition, right? How factor addition works. So for the addition factor to happen, yeah, they have to form a parallelogram. All right, but then what else do we know? We also know these two are equal, right? So equal radii. So what we can say that this is a rhombus, isn't it? My writing is not the best today, so basically in a nutshell, we'll say, okay, we've got a parallelogram because that's the addition factor with of these two factors, and we're given they are equal, making this one has to be a rhombus, so you have equal adjacent sides. Okay, so well, how does that help us? So that means that's R, making these guys equilateral triangles. Okay, so I'll just continue down here. Okay, so that means angle COA is equals to angle COB is equals to pi on 3. Yeah, the angles of an equilateral triangle. So therefore, angle AOB is 2 pi on 3. Just add them together. All right, so that's more or less it. Moving on, hence show that now, as I go through this exam question, I'll also sort of start to point out these very specific HSC terminology or HSC keywords, right? The word hence means you should use the prior part to assist you. In fact, hence kind of insists that you use the prior part, right? So you have to think, okay, they got me to find an angle. How is that relevant? So let's put that in, 2 pi on 3. Okay, well, if I know the angle between two factors, you can think of it as a rotation of factors. Now, if you didn't know this already, so if you want to, for example, rotate Z anti-clockwise by theta, for example, you just simply multiply Z by cis theta. That's how you rotate a vector. That's not 90 degrees. If it's 90 degrees, just times I, any other angle, cis that angle, okay? But if you want to do clockwise, I'll just throw it out there in case you need it. You times it by also cis, but negative the angle. So just imagine anti-clockwise, positive angle, clockwise, negative angle. I know it sounds very counterintuitive. Okay, so with that in mind, so that's where I'll explore. Maybe you're like, I don't know how that leads to that result, but let's start with that. So we've got, let's come back to the diagram first, because you probably can't see what I can see. So OB is OA rotated 2 pi on 3. Right, 2 pi on 3. So in other words, OB represented W and OA represented Z, so times cis 2 pi on 3. So that's the start. Okay, so then am I trying to prove that? Well, let's try cubing it and see what happens. And the Morse theorem, multiply the indices into it. That looks terrible. Hold on. All right, so the 3 cancels. Cis 2 pi. And what is cis 2 pi? Cis 2 pi is 1. Okay, that's it. That wasn't so hard, right? Let's have a look at the third part. So the third part is showed that. Now, if I think as extension to students, this is how I see the program, right? You've got the core syllabus, but as you look at a lot of exam papers or even how your school writes the exam, they don't always stick strictly to what is the core syllabus, right? They can always sort of go beyond that and test you sort of, you know, skills as sort of that problem solving skills, being able to connect information together that you're supposed to be able to do just based on the core syllabus content, okay? And that means you have to sort of go broad and wide in terms of your mathematical knowledge. So you're able to spot patterns. And I feel like this is one of those things. If you know what the difference of 2 cube factorization looks like, this one should be super easy peasy, right? So what I mean by the difference of 2 cubes factorization is if you have a cubed minus b cubed is a minus b, a squared plus ab plus b squared. Yeah, so while strictly this is obviously not in the extension 2 syllabus, technically it was in the original sort of 2-unit syllabus that was also removed for some strange reason. Doesn't matter, know this stuff, right? Otherwise you won't be able to spot some very, very obvious patterns. So in this case, applying that to, with that as the starting point, okay? So move it to one side, factorize in the same way. Okay, so now this suggests either this equals to 0 or this equals to 0. Now I can conclude it's the second case, and I'll show you why. All right, so that is equals to 0 because Z and W are not the same point. Okay, so the first one doesn't actually work for this one. All right, so that's it. So you just need to justify that. So I'm hoping that makes sense. So the first part, let's summarize. First part is just geometry reasoning, yeah, because that's the addition factor that makes this parallelogram, and the fact that it has equal adjacent sides makes it one step further a rhombus. And in fact, it's the equilateral triangle as a result because OC has the same length as OA and OB. Then the second part is just using that rotation relationship and then cubing the result. And then the third part is then it's not so much to do with complex numbers, it's just like algebra and factorization. That's all it is. All right, so moving on. What have we got here? So we've got Z is cos theta plus I sine theta on the diagram. A represents Z, B represents Z squared, and C represents Z plus Z squared. Okay, so that's the addition factor, meaning if I join this up, this is a parallelogram. Okay, all right, so explain why the parallelogram OACB is a rhombus. Okay, so now we know it's not just a parallelogram, it's a rhombus actually. So rhombus main defining feature is equal sides, right? So that's what you will be looking for. Now, in this case, whenever I present this question to students, they often miss a very important fact why this is a rhombus. And they're doing these massive calculations, trying to calculate it. And then once I pointed out, it's super easy. All right, I might just, give you a moment to see if you can spot what the length of these guys are. I'll pause the video. Yeah, I'll give you 5 seconds. All right, have you got the answer? So, those of you who are keen observers, you may have noticed that Z is cos theta plus I sin theta. I know most people will just read it, oh yeah, that's just the standard form. No, not quite, because let me just write the shorthand for that. Cis theta. Cis theta is a modulus of 1. So in fact, this is 1, okay? Which means Z squared. So if Z is equals to cis theta, then Z squared is equals to cis theta squared, which makes it cis 2 theta using De Mor's theorem, which also has a modulus of 1. Okay, that's the trick. All right, so modulus of Z is equal to modulus of Z squared, which is equals 1. So therefore, OA is equals to OB equals to 1. Therefore, OACB is a rhombus. All right, so tricky, huh? But well done to those of you who spot this. Yeah, well done. You're in the minority. All right, so second part, show argument of z plus z squared. So which vector is z plus z squared? OC, right? So you're looking for, let me use red. You're looking for this angle here, okay? What I'm going to do, I might actually copy this because it's a bit hard to explain this without the diagram. So let's copy these and let's do this. Okay. All right, so the second part is to find the argument of that vector OC. All right, well, let's start with, well, we already said z square is cis 2 theta, right? So that means, let's call that x. So angle BOX is equals to 2 theta. That's what it means, okay? And angle, I'll just write it. All right, Z is cis theta, Z squared is cis 2 theta, so AOX is theta. So therefore, angle BOA is 2 theta minus theta, which makes this theta. Okay, so this bit here is theta. Okay, and then that means angle COA is theta on 2, diagonal bisects vertex. Angle in rhombus. Alright, so therefore angle COX is theta on 2 plus theta, which is 3 theta on 2. So that means argument Z plus Z squared is equal to 3 theta on 2. Done. Okay, so I probably wrote more than I need to, but that's just to show you the thinking. All right, modulus. So modulus is the length of OC, right? So let's copy this guy. All right, so we're looking for the modulus of Z plus Z squared, which is the length of OC, okay? Now, what a lot of people forget is vectors is not actually, you know, in its own vacuum. You've got a lot of foundational knowledge, right? Like trigonometry, geometry, coordinate geometry, all of that basic knowledge. Yeah, that should support you in your understanding of vectors. So this is one of those instances where you should call upon that knowledge because you're trying to find the length of this and it looks like you don't know much. But if I look at the triangle OCA, right? Because that's where OC exists. I know this is 1. I know this is 1. I know this is theta on 2. I'm trying to find the length of that. Well, naturally, that's going to be theta on 2, by the way. So you can use cosine rule, right, to find this if you need to. You can absolutely use cosine rule. Now, I'm going to take it one step further. Instead of using cosine rule, I'm going to draw in the other diagonal, and they're going to be naturally perpendicular because you've got a rhombus. Rhombus have perpendicular bisecting diagonals. That turns it into an even easier calculation, right angle triangle. Okay, so I'm going to find OM and then double that and you'll get OC. Okay, so let's start with cosine. So cosine theta on 2 is equal to adjacent over hypotenuse, so OM on OA, which is OM on 1. So that means OM is equal to 1 cos theta on 2. Okay, so after that, well, OC is equal to 2 OM since diagonals bisect each other. Right, so 2 cos theta on 2. So that means that's it. So easy and simple, isn't it? Now, I've done this with cosine rule as well before, so you can absolutely do that as well, but that is the shortest way there. All right, next. By considering the real parts of z plus z squared or otherwise, deduce this. Now, think about, well, where is the examiner trying to take you on this, right? They got you to find the argument of z plus z squared, the modulus, right? And you can see components of that on the right side. So I would think, okay, is there another way of expressing z plus z squared? Well, absolutely, because we actually have the original values of z plus z squared. So let's have a look at that. So what I might do is this, actually. I'm going to copy this entire bit. Okay. All right, so z plus z squared itself is cis theta plus cis 2 theta, right? So that's cos plus I sine, cos plus I sine, right? So the real part is cos theta plus cos 2 theta. Okay, you can see that is basically this part. Okay, so now the other expression using part 2 and 3 to assist us, we can see that z plus z squared is also equal to modulus argument, right? So modulus of that times cis 3 theta on 2. So the real part is that times that. Okay, so that is equal to that. And that's it. That's simple. It looks complicated, but it's incredibly simple. And I think that's the trick about exam questions slash HSC questions. You need to think about where the examiner is trying to take you. They don't ask you to do stuff for no apparent reason. The better you become at reading the mind of the examiner when they write the question, where are they trying to lead you with the breadcrumbs, right? The better you are able to answer a lot of these exam questions. So that's what I find with a lot of students. So just start working on that and developing that sort of that sense of where are they trying to take you with that question. All right, moving on. 217, that's a pretty recent one. This one's a tough one if you don't have a thorough understanding of vectors. I mean, it's in question 13E, so it's kind of in the middle of the paper, but if you're not strong with vectors, this one's going to be really, really difficult. All right, so let's have a look. A, B, C, D on the Argand diagram represents A, B, C, D as a square. And then it goes by using vectors or otherwise, show C is that. Now, most students will look at this like, holy crap, where do I start? All right, so you need to, I will suggest use the square. There's actually many ways you can attempt this, and I'll just show you one of the ways to attempt this. Now, I just noticed when I attempted this first time, I didn't notice that they put the right angle here. Yeah, maybe they've deliberately put that right angle there, so you want to look at, these two vectors as rotation vectors. I don't know, maybe that's what they want you to do. All right, in any case, I'll just show you my method, and then you can try that method as well, just to see, because sometimes they're sneaky like that, right? They put in, like, why are you putting that right angle there? Not there, not there, not there. There might be like a hint in that, right? Okay, so before I dive into that, I want to talk about vector subtraction, because if you don't understand how these vectors are built, then it's going to be hard. So let's say we have the point C and D, for example. Here. It's better. Right, so C, D. Okay, so if I drew the position vectors, right, like that, okay, and we apply the parallelogram rule to it, remember what I said, this vector here is the addition vector, but the other diagonal is the subtraction vector. And in fact, if it's pointing towards C, it will be C minus D. Okay, so that understanding is important. So how you build these vectors, they are what we call free vectors. Free vectors are vectors you don't know the value of by just reading it, because it's not really pointing to the correct point, right? You have to think about moving that back down here and see, well, what it is, right, as a position vector. Now, obviously, you don't have the luxury to do that here. That's a bit stupid to do that anyways. So this is my tip, all right? So this is my tip. If you have a vector that joins any two random points on the number plane, it's always a subtraction vector, and the subtraction vector is from wherever the arrowhead is. So in this case, C minus the tail end. Arrowhead minus tail end. That's how you know what that vector represents. So All right, so I hope you know what I mean by arrowhead minus tail. Okay, so it's the, for example, if it's pointing this way, yeah, or I have it here pointing that way, it's C minus D. Okay, all right, so with that in mind, let's do a new page. That's good. Okay. So what I'm going to do is, just from an orientation perspective, I know we're way more used to sort of working vectors in those directions. I'm just going to work it in that direction. So I'm going to use this angle instead of the angle they randomly drew in. Okay, so first of all, if you look at this, now why I did this is because that makes C the addition vector. Okay, and I think it's a little bit easier to build. So I can see that, let me just make a statement first. All right, so AC is AD plus AB, right? Addition factors. Now, what they each represent, remember that little trick? So arrowhead minus tail, so that is, oops, D minus A, and AB, B minus A, and AC, C minus A. Nice and easy, right? Look at the vector, you know what it is immediately. Now, another thing is, if you look at the expression you're trying to prove, so firstly, there is no b, so you need to find a way to get rid of the b. Now, the second thing is, they gave you the fact that this is squared, so you probably should utilize it. So the most common way to use a square is sort of, well, the right angle equals side, so it's like a 90-degree rotation, so I can see that AB is equals to AD times I, right? Rotated 90 degrees anti-clockwise. So equals to D minus AI. Okay, so in other words, I can replace. So I'll just leave that there. B minus A, which is AB, yeah, with D minus AI. Okay, so now with that as my starting point, that looks good because I only want CDA, right? And I only have CDA now. So let's simplify this. So C is D minus A. I'm going to add that A across so they cancel. And then factorize that. That's pretty much it. Wasn't a very difficult 2 marks, but that's assuming you know vectors very well. I think, you know, that's the main thing that holds a lot of students back from getting those 2 marks. All right, last question. Those are students who are in my class, they look at this and very laughing. So I throw this into my quiz question every year. And then every year, no one gets it right on the first go. And it's hilarious because once I show them how easy the working is, they feel a little bit ripped off. So if you want to take on my challenge, pause the video right now. Give it a go, right? Spend 10 minutes, right? If you're like, after 10 minutes, you're like, nah, I couldn't get it, but I'm so determined. Yeah, just keep going, keep trying until you get it. Or you can just wait for me to reveal the answer and how simple it is. All right, let's get into it. We've got point P. On the diagram represents the complex number Z. The points Q and R. Q is that. R is that. And your given W is that thing, and M is the midpoint of QR. All right, so find the complex number of M in terms of Z. Now, there are so many ways to think about this problem. You're like, oh, it's the midpoint of this line, and you've got a parallelogram. I think if you start really looking into it from memory, that is actually an equilateral triangle of sorts. There are so many ways to sort of understand what is given to you is almost confusing as to where you should start. So before I actually give away the answer, I just want to talk about something. Let's say I've got 2 points. 1 plus 2i, and let's say I've got another point minus 1 minus 1i. Yeah, just keeping things very simple. Now, if these were coordinates, right? As coordinates, that's 1, 2. As coordinates, that's minus 1, minus 1. If I ask you to find a midpoint, you're like, oh yeah, that's like super easy. Midpoint formula, right? Minus 1 plus 1 on 2, minus 1 plus 2 on 2, right? So that's 0, a half, piece of cake. But what I want you to draw your attention to is the fact that, well, the way complex number works are like coordinates, right? So if I ask you to find the complex number it represents, you add the two numbers together and half it, right? Just like how a midpoint formula would work. And you gather your real and imaginary parts together. So that's 0 plus half I, or just half I in this case. Okay, so that's the first point I want to make. Points on, sorry, let me rephrase that. Complex numbers, yeah, represented as points on the Argand diagram operates a bit like coordinates on a Cartesian plane. So coordinate geometry applies. So in answering the first one, if you've spent half an hour trying to work this out, you will be furious to find that I'm simply just gonna average the two. I hope you're not too angry. Okay. It's like, oh yeah, that's great, but how the heck do I add this? Well, very simple. Let's factorize it out. And the funny thing is you actually know what they are, right? Because you know what W is. And in fact, you can use the property, right? If you have a complex number, you plus its conjugate is always the two real parts. So that's actually what I'm going to do. So two real part. So real part is cos 2 pi 3. And that's negative a half. I hope you're mind blown. Or maybe you worked it out, smarty pants. Alright, so second part. Now that you've seen the first part and how easy it was, right? Maybe pause for another 5 minutes and see if you can work out the second part yourself. I promise you the second part is super, super simple if you use the technique I just showed you. Now, if you want to find out the answer, let me show you now. So let's come back and join this together. So point S is chosen so that PQSR is a parallelogram. Find this complex number. Okay, the point is in a parallelogram, diagonals bisect each other. So the midpoint of QR is going to be also the midpoint of SP. That's the first point. So I'm just going to, yeah, let's add a page. Actually, what I'll do is, let's copy the diagram as well. Okay. All right. All right, so M is also the midpoint of SP. Okay, meaning S plus P on 2, so doing the average technique should equals to M. right? So S plus Z, so that's the complex number it represents, and M was minus a half Z. All right, so times 2 minus 2Z. Was that easy? Oh, easy, right? I knew you got it. We get there eventually. Okay, so I hope through this problem, so you can see it's not a hard problem if you know what you're doing. And I think factors in general, once you understand what you're doing, is not hard. All right, so, well, first of all, hopefully I feel that if you were confused before watching this lesson, this has cleared up some clouds around how factors operate when it comes to complex numbers. Or you maybe just, did it on your own without my help, and, congratulations on doing that. I hope you actually got the practice you need, and that's going to help you with your first assessment. Now, if you have any questions, comments, or, topics you would like me to cover, just leave a comment down below. You can also check out our website. We've got quite a few of these similar modules ranging from 2-unit topics all the way to extension 1 topics, and I think this is our first extension 2 topic. I'm hoping that's helping you, and if you have any questions at all, contact us by Facebook, email, website, your choice. Hopefully I can help you. Best of luck with your assessments, and keep an eye out for our next module, also on complex numbers. Bye for now.